Good evening. On May the 21st, there was a partial eclipse of the sun. I mentioned it last month. It was seen from Scotland, not from England, also from Scandinavia, and Nick James took this picture of it. It wasn't actually total anywhere, but I thought you'd like to see it. Now, a most interesting and important thing has just happened. Or rather, it actually happened more than 8 million years ago, but we've only just known about it. There's been a supernova outburst in the spiral galaxy M81, or Messier 81. Now, there are plenty of spiral galaxies. Our own galaxy is a spiral, and this one is fairly easy to find. You can see it as a dim blur with binoculars. And it lies in the constellation of Ursa Major, the Great Bear, and here's rather a lovely picture of the main stars in the Great Bear, taken by Dame Kathleen Ollerenshaw. I think everyone can recognize those. So let's find M81. Locate the bear, then find the star Upsilon Ursae Majoris, magnitude 4. Close beside that, a star called 23. Then a little group of 3, 1, 2, 3. And then the star 24, below magnitude 4. And M81 is in the same binocular field with that star. And you can see it with binoculars as a dim blur. I may say, not very far away from it, is a much smaller irregular galaxy, Messier 82, but frankly, I can't see that with binoculars. M81 on the bottom there, M83 on the other top. But it's M81 that interests us now. And here's a picture of it in its normal guise. And here's a picture taken by Ron Arbour showing the supernova. You can see it there. It's flared up, and it became magnitude 10, so you could see it with binoculars. And Denis Buzinski at the Condor Brow Observatory took this picture of it for us, and there's a supernova indicated by an arrow. And this is really very important. It is the brightest supernova since the invention of the telescope, with the single exception of the outburst in the Large Cloud of Magellan way back in 1987. We did several programs about that. And there's a picture of the large cloud. On the end of the arrow, the progenitor star, and this is what happened to it. And that did become easily visible to the naked eye, although, unfortunately, it was too far south to be seen from England or anywhere in Europe. Now, supernovae are colossal stellar outbursts, the greatest explosions known anywhere in nature. At this stage, I'm delighted to introduce Dr. Robin Catchpole at the Royal Greenwich Observatory, who is working very closely with this supernova, as he was indeed on the last one. First of all, Robin, welcome to the sky tonight.
Thank you,
And
Patrick.
what exactly is a supernova?
Well, a supernova is the name astronomers give to the rare but awe-inspiring event when an entire star explodes. The amount of energy released is absolutely colossal, and it's equivalent to the entire energy generated by a galaxy of several thousand million stars for over several years. But in fact, only a small amount of this energy actually comes out as light. 99% of the energy is lost in neutrinos, and these were in fact detected in the case of 1987A. That leaves 1% of the energy, which 99% of that 1% comes out as kinetic energy. And the energies again are rather colossal. 1 gram of this expanding material has the energy equivalent of 2 tons of TNT. So that leaves only 1% of 1% finally to be detected as radiation by our telescopes. Now, supernovae are very important. They hold a vital place in the ecology of the universe. First of all, they actually create heavy elements. And in fact, all the elements that you can see, the cameras and the table in this studio, were all actually manufactured in a supernova explosion. And in fact, they've probably been through several explosions. The other importance they hold in astronomy is that the shock waves from the expanding supernova actually trigger star formation.
So supernovae really are of tremendous importance.
Yes, indeed. I mean, as far as astronomers are concerned, they have a vital role in deciding how a galaxy evolves. From the physics point of view, they pose a great challenge to physicists to explain the details of the explosion. And, of course, for astronomers, they provide a test of stellar evolution theory. And lastly, they hold out the hope of providing a calibration of distance. Because they are so luminous, they can be seen very deep into the universe.
But they aren't all alike. I mean, there are 2 definite types.
Yes, there are 2 types of supernovae, which astronomers rather unimaginatively refer to as types 1 and 2. In a type 1 explosion, you have a double star. One of the stars is highly evolved, and the companion dumps over a certain amount of material onto this evolved star so that it exceeds a certain critical mass, and then the whole thing burns in an instant to cause a huge explosion. Now, the advantage of a type 1 is that we think that they always go off with the same size bang, so they hold out hope as distance indicators. Now, type 2 explosions occur only in massive stars, more massive than the Sun, and in that case, the whole star just explodes.
And we have seen plenty of those.
Oh yes, the brightest supernova to be seen since, as you mentioned, since the invention of the telescope, was actually in the Large Magellanic Cloud. And when that explosion took place, or rather when the light got to the Earth, I was very fortunate to be working in South Africa. So I not only saw the explosion, but I actually spent quite a lot of my time doing research on that supernova. So you can imagine I felt rather pleased to be back in England working at the Royal Greenwich Observatory for this one.
Very indeed. Well, this was a type 2 supernova, wasn't it, this one?
Yes, they were both type 2 supernova, this one and the previous one.
The explosion of a very massive star, what actually makes it explode?
Well, you can say that the history of a star is the history of its fight against the forces of gravity. It's the gravity that causes the initial cloud to contract and start to condense into a star, about 15 million years ago in this case, probably. It's gravity that finally heats the center of this contracting object hot enough to ignite hydrogen, so that hydrogen starts to burn into helium. And then from there onwards, it's the successive burnings of nuclear fuels merely to delay the moment when the supernova comes. And we can follow the evolution of hydrogen burning to helium, forming an inert helium core, and then when that is finished, the core contracts, it's heated up a bit more, finally the helium ignites, and at that stage the star becomes a red supergiant. And it's important to realize that it's the outer layers of the star that tell us what it's like, but it's the inner layers that govern its future. And so we have a situation where successive increasing fuels of increasing atomic weight are compressed and ignited at the core of this star until we get to the situation where we have an onion-like structure. We have a solid iron core in the middle, and then we have successive layers on top of that where successively lighter and lighter elements are being burned, as we can see in the diagram here. And on the outside, we still have some unburned hydrogen. Now this diagram shows the situation very, very shortly before the final crunch comes. And the final crunch comes because iron won't burn, or rather, when iron burns, it doesn't actually give out any heat. It in fact absorbs heat. So suddenly, from having this enormously hot silicon core, we find we have an iron core that collapses from about 5,000 kilometers in diameter down to only 10 kilometers in diameter to form a neutron star. The temperatures are absolutely colossal. They're tens of thousands of millions of degrees. The density is enormous. As the star collapses, as the neutron star is formed, the outer layers are no longer supported, so they fall inwards. They hit the neutron star, they bounce, an enormous shock wave is generated. This shock wave passes out through the surface towards the surface of the star, liberating neutrinos, and finally the bang. Here it comes. The shock wave has reached the surface of the star. The whole thing has gone bang.
Pretty dramatic. Well, that's the principle. Now, what about this particular supernova, 1993J in Messier 81?
Yes, this supernova was first seen by a Spanish amateur astronomer called Garcia Diez at about 10:30 on Sunday the 28th of March. By Monday evening, news had been passed to our telescopes on La Palma, and by that night, just after sunset, the Isaac Newton telescope was pointed at the supernova and the first spectrum was being obtained. At the same time, news was being flashed around the world and other observatories were starting their observations. As you know, the observatory on La Palma and the Royal Greenwich Observatory are very closely related. And staff at both these establishments realized that if we were to obtain complete coverage and reduce the data and make it available to the astronomical community as soon as possible, then we would need to have very close collaboration. And we arranged that visitors using the telescopes, for instance, the Johannes Kapteyn telescope that took a lot of the photographs and obtained the photometry, would be asked to give up some of their hard-won observing time. And even the Carlsberg Transit Circle was brought in to make observations.
After all, M81 is only about 8 million light years away, and as galaxies go, that's pretty close, so it's very often studied for totally different reasons.
Oh yes, well, we're very fortunate that there's basically quite a lot of people are interested in that galaxy, and what transpired was that an observation had been made half a day earlier than the Discovery observation that showed it was already brightening. So we can be fairly confident in saying that the core collapse occurred sometime late on Saturday night, and it started to brighten Sunday morning, of course, minus the 8 million years that it took the light to get to us. We were also very fortunate in that we had an image taken with the Isaac Newton telescope some years before of the field of the supernova. And if you look slightly to the right of center on the image you can see on the screen now, you see a very faint star at magnitude 20. And if we compare that with an image taken shortly after the explosion, you will see how that star has brightened, and there's our supernova. In fact, it turns out to be the blend of two stars. We think that primordial image is in fact the blend of two stars, and they were two supergiants.
Were they red or blue or which?
Well, they were both reddish, probably red and yellow, but not blue this time.
What about the peak luminosity? How much brighter than the sun?
Well, their peak luminosity was something like, well, in excess of 187,000 million times the luminosity of the sun.
It's quite incredible, isn't it? Robin, you've been studying the light curve. Has that told you really what's going on?
Yes, the light curve really gives us all the clues. And here we see a visible light curve showing the initial rapid rise, rapid decline, and then slow rise to a secondary maximum. And this is really the secret of, tells us the secret of what's going on here. The first rapid decline is caused by the atmosphere of the star expanding and cooling, and then the second maximum is caused by the escape of energy from the radioactive materials that were actually generated in the explosion. And in fact, what we can do is combine data obtained over several wavelengths and produce what we call a bolometric light curve, which we see on the screen here. And you can see how the luminosity again decreased and increased and then faded away. And we can compare that with 1987A, and here they are on exactly the same scale of brightness. And you can see they are fundamentally different. They have the same sort of shape, but the time scales are quite different. And this is due to the fact that 1993 had a very, very thin outer atmosphere, and this is due to the fact that there was a companion star that took away most of that atmosphere before the explosion. Now, there is one similarity between the two explosions, and that is in the amount of nickel-56 that seems to have been generated in the explosion. And if you look at the dotted line there, you will see the radioactive decay curve of 25,000 Earth masses of nickel-56 decays into cobalt-56 that was generated in the explosion. And you will also see the extraordinary coincidence 1993J and 1987A lie on the same curve. And I'm assured by my theoretician friends at Cambridge that this is coincidence, because if it isn't coincidence, it means we've got the physics completely wrong.
What have you learned from the spectrum?
We can tell a great deal from the spectrum, and just to illustrate that point, I'd like to have a quick look at the spectrum of something on Earth. And here we have a view of a street scene, and you will see the street lights on the right-hand side, and to the left you will see the spectrum of those lights. In other words, what we've done is to put a grating in front of our camera here, and we have broken up the light from the street lamp into its characteristic colors. And you will see that those colors obtain what we would call as sharp emission lines. And these emission lines are the unique signature of a particular element, and in this case it's the signature of the element mercury that's in those particular street lights. Now, when we look at a spectrum of, for instance, a supernova, we can tell an enormous amount. We can tell how hot the thing is, how fast it's going, and how much what it's made of. And here we're going to look at we're looking at a few supernova spectra. We see the emergence of the helium lines, and then eventually the hydrogen lines, and even the calcium and the sodium lines that you're familiar with in the street lamps. And you will see how the emission line intensities change, and we can tell a great deal about how fast that material is moving. It's expanding at something like 15,000 kilometers a second, and we can tell how the whole shell is expanding and fading away.
The fact that this is a fairly nearby galaxy is very convenient.
Yes, it is, indeed. Even though it's far too faint to see with the naked eye, it is almost too bright to observe with the William Herschel telescope. And this enables us to do something very interesting, and that is to look at the spectrum at very high resolution. And if we concentrate on just this one small part of the spectrum where we see the sodium D lines in absorption, then we can expand that and look at it at much greater detail. And here we are going to focus on that one little blip marked sodium, which is in fact the signature of interstellar sodium. And we're going to look at that at very much higher resolution with the aid of the William Herschel telescope. And what we see when we do that is a series of absorption dips. Instead of just seeing one line that we would expect to see here, we see three groups of lines. And we can also look at calcium, which is down in the violet part of the spectrum, and we see a more or less similar grouping of lines. And what's very interesting about this is that these break up into three groups. The negative velocity group are arising within the spiral arms of M81, while the central group of lines comes from our own galaxy. And most interesting of all, we see a group at positive redshift, which we think are associated with material in the intergalactic space.
Obviously, you're working very closely with other observatories.
Yes, we are. In fact, observatories throughout the Northern Hemisphere are making very extensive spectroscopic and photometric observations of the supernova, and it's also being observed at other wavelengths. For instance, the Ryle telescope is observing in the radio, ROSAT is observing in the X-ray, and we expect interesting things to develop later on there, and IUE is observing in the ultraviolet.
Well, the supernova is now fading. What's going to happen to it next?
Well, we will go on monitoring the spectrum and its brightness for some time, but then there's an interesting prediction, and that is that this supernova also contains an annulus of material very similar to the one seen around 1987A and photographed by the Hubble Space Telescope. And we expect to see evidence of this in our spectra in 6 months' time or so, and eventually the shock front will get there.
We say that M81 is close, but it is more than 8 million light years away. What would this supernova look like if you could see it from much closer range?
Well, if we want to know that, we should look in our own galaxy, and we can look at some supernova remnants there. The youngest is probably Cas A, which is only 300 years old, and it's still expanding and looks like an explosion. A bit older, at 900 years, is the Crab Nebula that contains a pulsar. At the order of a few thousand years, we come to the Vela supernova remnant, and at an age of 40,000 years, we see the Veil supernova remnant. And here we see material really returning to interstellar space, ready to form the next generation of stars, where it will be born, for instance, in the Orion Nebula, where another generation of stars is being born, and indeed, within the next million years, most of those bright stars will also have become supernovae.
I wonder what 1993J will look like then. Anyway, it is telling us a great deal. Robin, thank you very much.
Thank you, Patrick.
And don't forget, if you want the latest information, then simply dial our information line, 0898 666 000. And when I come back next month, I'm going to give you the very latest news on the repair mission to be sent up next December to the Hubble Space Telescope. So until then, good night.